The last lecture video probably won the most number of equations in one video award, albeit they were all derived from merely a handful of principles: the ideal gas equation, the internal energy, the work done by gas, and first law of thermodynamics. So I think it's worthwhile to recap this equation in tabular manner. We learned three thermodynamics processes. Each refer to a particular situation whereby one of the three microscopic states that describe a gas system, namely pressure, volume, or temperature, is kept constant. These microscopic states are the parameters for the three terms in the first law of thermodynamics, namely change in internal energy, work done, and heat that flows in or out of the system. The first law of thermodynamics guarantees that, regardless of which thermodynamics process a gas system undergoes, energy is conserved. That's after all what first law of thermodynamics essentially is, the conservation law of energy. Let us start with the zeros. By definition, isochloric involves no change in volume, whereas isothermic involves no change in temperature. This implies that work done and change in internal energy are zero in isochloric and isothermic process respectively. The change in internal energy for n mole of gas is generally given by 3/2 times n times r times change in temperature. Internal energy depends solely on temperature of the gas and not the process it undergoes. Hence, the equation to describe the change in internal energy during isobaric and isochloric process is the same: 3/2 times n times r times change in temperature. If we wish, we can recast this equation in terms of pressure and volume using the ideal gas equation PV equal to nRT. Work done is given by integrating pressure of a change in volume. In isobaric process, it's easy because pressure is constant. In isothermic process, it's slightly more complicated, but I provided the step-by-step derivation in the last video. Finally, from first law of thermodynamics, heat that goes in or out of the system is simply the sum of the previous two terms on top. This completes our table, for now. Looking at this table, I hope you guys, same as me, immediately realize there is something missing. Or rather, the table looks incomplete. We have 0 for W and delta U. Is there then any such process whereby Q is 0? In other words, is there any such process whereby the states of the gas system change, yet no heat flows in or out of the system? Well, there indeed is. Such process goes by the name adiabatic. The PV diagram of an adiabatic process is shown here. At a glance, it reminds us of the PV diagram of an isothermic process, but there is a subtle difference between the two, which we will discuss later in this video. Because the process does not involve any heat exchange with the environment, energy will only be exchanged or converted between mechanical work and internal energy. In other words, the work done by the gas in an adiabatic process is equal to the negative change in internal energy of the process. Hence, we can compute this work done indirectly from the change in internal energy, whose equation is well known. I do not recommend to derive the work done in an adiabatic expansion directly from first principle by integrating pressure of a change in volume, for a reason which will be made obvious pretty soon. But if so wish, we can recast the equation in terms of pressure and volume as well. Now, why do I not recommend to derive the work done directly from first principle by integrating pressure of a change in volume? We could do so in isothermic process. Why can't we do the same here? Well, the answer is, unlike in isothermic, whereby temperature is constant, in adiabatic, all pressure, volume, and temperature have to change. There is no way you can isolate the system in such a way that it does not exchange heat with the environment, and yet you can still do something on it while conserving one or more of the three parameters. No way. So unlike in isothermic, where we could recast pressure as a function of volume solely, since temperature is constant and thereby it could be taken out of the integration, and we have a simple integration to solve, in adiabatic, the temperature is not constant. It can't be taken out of the integration, which makes the integration complicated. Having said that, though all pressure, volume, and temperature change, if the gas does not leak, if the number of gas particles inside the container is conserved, then we will have this relationship between the final and initial state of the gas system, as we learned in lecture 11.1. However, we also have the ideal gas equation. The ideal gas equation essentially describes how one of the three states behave in terms of the other two. So although pressure, volume, and temperature all evolve in an adiabatic process, they do not evolve independently of one another. The behavior of the gas inside the container must fulfill these two equations, which in turn, the two equations provide a constraint on how the states evolve. Or, think of this from another point of view. Think of these two equations as simultaneous equations, whereby there are three unknowns, namely P, V, and T, but we have only two independent equations. Of course, we cannot solve the equations completely for P, V, and T. We need 3 independent equations to solve 3 unknowns, by the way. But we can at least eliminate one of these states. Let's say we decide to eliminate temperature from the equation. With some algebra, we can arrive at the following relationship between pressure and volume. The power gamma refers to the ratio of the gas heat capacity at constant pressure to that at constant volume. For a while, I was considering whether to include the step-by-step derivation of the latter equation, but decided against it as it involves calculus. If you wish, just like when deriving the work done in isothermic expansion, you may take the latter equation in its final product. For those who are interested and have calculus background, you may follow through the derivation here. Also, there is nothing to prevent us from rewriting the latter equation in terms of pressure and temperature, or volume and temperature. Remember, with 3 unknowns and 2 equations, we can always eliminate one of the unknowns. However, I purposely choose to present the latter equation in terms of pressure and volume, so that we can compare adiabatic expansion to isothermic expansion. If both start from the same initial state, the power of gamma in the adiabatic process causes its plot of pressure against volume in the PV diagram to draw faster or steeper than the isothermic. So yes, as we always see it printed on the t-shirt, the PV diagram for adiabatic and isothermic process are same but different. So that's it. We can finally complete the summary table we began with. Behold, 4 thermodynamic processes and 3 terms from the first law of thermodynamics.